Example 3.3. The RMS speed of the molecules in a 1 gram of hydrogen gas is 1800 meters per second. A. What is the total translational kinetic energy of this gas molecules? What is the internal energy of the gas? And C. If 500 joules of work are done to compress the gas, while in the same process 1200 joules of heat are transferred from the gas to the environment, afterwards, what is the RMS speed of these molecules? The translational kinetic energy, K trans, is not the same as the internal energy, because the internal energy is the total kinetic energy. And by the equipartition theorem, they have to be quadratic. So you can get K translation, K rotation, K vibration, and on here. As long as they're quadratic terms, then they get distributed equally. But typically, what this really means is that you only see K rotational if the energy is high enough. If it's not high enough, it stays at K translational. And that's because the energy for rotations will die off exponentially, so that you really don't see that very much. So now, since H2 gas is diatomic, we immediately know that CV, which is 5/2 RT, it has 5 degrees of freedom, where the internal energy is then going to be 5/2 N RT. However, the RMS speed is only represented in K translational, which of course is equal to 1/2 mv RMS squared. And in this case, because we're talking about hydrogen gas, they tell us that VRMS is 1800 meters per second. So now let's go look at that. A, what is the total translational kinetic energy of the gas molecules? So then let's look at that. So now we want the total translational kinetic energy, K trans. So each diatomic molecule has some RMS kinetic energy. So let's be careful how we define this. So each diatomic H2 molecule has a K RMS, which then implies a V RMS. The total K translational is the sum of all H2 molecule. H2 molecules kinetic energy. So when I write this down, I could then say that the total translational kinetic energy then should be the number of hydrogen gas molecules times their individual RMS kinetic energy. So when I look at this guy, then this is going to be the number, and then this tells us here is that this is going to be 1/2 mv RMS squared. Now, the thing that you got to be careful about is this. That mass, this is not a molar mass. So what you're seeing here is that what we really got to do here is that in order for us to calculate the total translational kinetic energy, so we need to determine, one, the mass of H2. Two, we got to calculate the number of H2 molecules, which we call NH2, and we then are going to calculate K translational. So we're going to do this over 3 steps. So let's do that first. So the first thing here, let's talk about the mass of an H2 molecule. So remember, these are not molar mass. So what we know here is that a hydrogen atom has a proton and an electron. The mass of an electron is 1/1800 times, so it's the mass of the proton is 1800 times the mass of the electron. So that means here I can ignore the mass of the electron. So the mass of H2, to a very good approximation, is then going to be the mass of H2, which will then be 2 times the mass of hydrogen, which will be the mass of the proton, plus the mass of the electron. But the mass of the electron is so small that we can ignore it. So then this is just 2 times the mass of a proton, which then is 2 times 1.67 times 10 to the minus 27 kilograms. And so this is then going to be 3.35 times 10 to the minus 27 kilograms. And that's our good approximation of the hydrogen gas mass molecule. So now that I have that, the next thing I got to calculate is the number of hydrogen molecules. So now we want the number of H2 molecules, which is, of course, H is this guy right here. So the way we do this here is that we do it the standard way. So the standard way here is that we start from the mass of our sample, and we get the molar mass, and then we get the number of moles. From the number of moles, we use Avogadro's relationship to get that. So here we go. So we have 1 gram of H2 molecules. So the mole number is then going to be N of H2. Then it's got to be the mass of the H2 gas divided by the molar mass of H2. So when I look at this thing, I have 2 hydrogen. And so then I see here that I have 1 gram. So when I compute that, I get 0.50 moles. So now I know my mole number. So now the number NH2 is then going to be given by NH2 is then going to be the mole number times Avogadro's number, which will then be, of course, half of Avogadro's number. And when I look at this thing, I get 3.01 times 10 to the 23 H2 molecules in this gas. So now I have my number. So now the last thing I got to do is calculate the total translational kinetic energy. So I got to put this all together now. So now if I look at this thing, I now see that the total translational kinetic energy, K trans, then goes like this. So K trans equals NH2 K RMS, which then gives me NH2 times 1/2 the mass of H2 times V RMS. And remember, V RMS is 1800. So if I just start to put in my numbers, here's what I get. So I have 3.01 times 10 to the 23 molecules times 1/2 times the mass, which we see here is 335. In this case, it's the mass is minus 27. And then I have my RMS speed, which is 1800 squared. And this should give me units of joules. So then if I compute this number, I'm going to get a number that reads 1.61 times 10 to the 3 joules, or it's 1.61 kilojoules for K translation. So now I've calculated my K translational energy. So now the next thing that we want to do here is that we want to calculate the internal energy. So now our B here, we want to calculate the translational kinetic energy. No, the total internal energy. So this is going to be the internal energy E internal. Now, this is a subtle point here. When we look at, so from the kinetic theory of gases, classical temperature depends only on the, what is it? Only on the translational kinetic energy of a single H2 molecule. Now, as I said before, if the energy is high enough to excite the other modes, like the rotational, vibrations, etc., then we have to include them. But at lower temperatures, at lower temperatures, these other modes are, how do I say this? Frozen out. Now remember, that word frozen out is tricky because it's really, their energies fall off exponentially, so you actually don't see them. So then the temperature is what must be calculated first. So let's do that. So then if I have, for a single molecule, I have K translational, and note, this is 3/2 kBt. Note that this is not 5/2, right? It is associated with that. So now what I'm going to do here is that I'm going to solve for temperature. So if I do that, then my temperature reads like this. So then my temperature relationship then reads, so I'm going to put K translational or K RMS, it's the same if we're talking about just the translational motion, then this should be 3 kb into 2, and then the translational is 1/2 mv RMS squared. Just a tiny bit of calculations. You could see that the 2's cancel out. So I'm really going to be plugging into this relationship. It's going to be mv squared RMS divided by 3 kb2. So now if I start putting in my numbers, here's what I'm going to get. I'm going to get 3.35. This is the mass, times the RMS, which is squared. And then I got to divide this by 3 times 1.38 times 10 to the minus 23 joules per Kelvin. So when the dust settles, I now know that my temperature is 260 Kelvin for this gas that has an RMS value. But remember, we needed the temperature, but we really want the internal energy. So here's where it gets tricky. The internal energy for a diatomic gas, according to the equipotential theorem, is related to the number of degrees of freedom for every quadratic terms. So in our case, that really means I get Vx squared, Vy squared, Vz squared. Then we have two rotations. Let's say that this is the azimuthal, and then this guy is the polar, which then gives us 5. Now, I didn't have to write this because we already stated that the internal energy, which is then CV delta T, that this was then going to be 5/2 nRT. We knew that, but I'm just reinforcing certain ideas here. So now that I have that, it goes like this. I put in my numbers, which will be 5/2, 0.5 mole. R is 8.31 joules per mole Kelvin. And then my temperature is going to be 260 Kelvin. This gives me a value of 2.7 times 10 to the 3 joules, or 2.7 kilojoules. And this tells me that this is the internal energy. So, as expected, E internal energy at this temperature is 2.7 kilojoules, which should be greater than K translational, because it's not the total energy of the system, is equal to 1.61 kilojoules. Okay? So that's exactly what we expected, and that's what we're seeing here. So now the last thing that we want to do here, so now that I have the internal energy, what I want to go do now is I want to do this last part C here. So look what we have. We have a process that has what? 500 joules of work while compressing a gas, so that's positive work. And then I have 1,200 joules of heat that is ejected out of the system. So now they want to say, if I take this gas through this process, what is the final temperature of these gas molecules? Okay, so let's go compute that here. So if I now summarize what I just said here, so a process takes the H2 gas that compresses it using work that's a positive 500 joules, right? It's going to speed it up, while ejecting 1,200 joules out of the gas. And it goes into the environment. So what is the new VRMS value? I know what we expect, right? So we expect that the VRMS, which is going to be 1,800 meters per second, should be higher than this new RMS, which I'm just going to write new after this process. So we expect that. So we better calculate something like that. So here we go. So the way I got to do this is I got to calculate the internal energy. From the internal energy, I calculate the temperature. From the temperature, I then can go calculate the RMS. So my process of thinking is I got to calculate this new internal energy, which then that tells me this new temperature, And then from this new temperature, I could then go in and calculate this new RMS. So let's go do that. So from the first law, we then see that the internal energy, which is heat plus work, is then going to be minus 1200 joules plus 500 joules, which then gives us minus 700 joules for the change in internal energy. Clearly, you see a decrease right here, right? So if I look at this thing, it's clear that there's a decrease in internal energy. And as we said before, that should give me a lower RMS speed. So that means here, because we have that, so here we go again. Remember, internal energy has 5 degrees of freedom. So then that means here is that the internal energy, this new one, is then going to be equal to 5/2 nR, and this is going to be the change in the temperature here. So now, if I solve for delta T, let me move this over because I'm going to need space. See if I can move this over a little bit. So now that I have that, then that means here that this delta T is then going to be, doing the algebra, it's going to be 2 times the change in internal energy, and that's going to be 5nR. Now, we already know that this is negative, so I'm just going to put that negative in there by hand. So let's calculate this thing. So this guy's going to be what? 5. The number of moles that we have is 1/2 mole. Our gas constant. And then I'm going to put this in. So this is going to be 2 times 700 joules. So when I compute this, this is 67.4 K. Now, because of the decrease in internal energy, there is a decrease in temperature. So here's where I'm going to put that minus in by hand. So I'm going to say here that the new temperature is going to be the initial temperature minus the change in temperature. So remember, I'm putting in this minus here by hand because I knew that had to be the case. So then this will be 260 K minus 67.4 K, and that gives me a new temperature of 193 K. So now I have my new temperature. So now finally, I can now calculate the new RMS. So from this lower temperature, the new RMS is given by the classical temperature. So the classical temperature says K translation. Remember, it could be K RMS. And this guy is going to equal to 3/2 kBT. Remember, that's really the equipartition theorem thinking, but this is also equal to KRMS, like this. So now what I'm going to do here is that I'm going to solve for the new RMS value. So now solving for V RMS new, then I'm going to find here is that this is really what? V RMS new is then going to equal to what? So no surprise, it should be what? 3 kBT new divided by the mass of H2. And so then if I start putting in my numbers, I see here that I'm going to get 3 times 1.38 times 10 to the minus 23 times 193. That's my new temperature. And then I have my mass, 3.35 times 10 to the minus 27 square rooted, and I get a value of 1540 meters per second, which is now the new RMS. And as expected, V RMS, the initial one, was equal to 1800 meters. After the process, which there was a reduction, you could see here is that this is 1540 meters per second, which agrees with what we expected.